Dr. Melvin Miles is an electrochemist, now retired from the United States Navy, where he spent a career in battery research. In 1989, he successfully reproduced the Fleischmann-Pons excess heat effect, a controversial form of fusion-sized heat energy generated by electrolyzed bits of metal and water in a test tube. Martin Fleischmann and Stanley Pons had found a way to generate nuclear power from water without the deadly radiation. Critics claimed it was impossible and held fast to their belief that atomic fusion could only occur in extreme environments, like the interior of stars. These hot fusion reactions produce nuclear products and radiation harmful to life. Researchers had reported nuclear products from cold fusion cells, but always in amounts millions of times less than hot fusion, and their production could not account for the amount of excess heat generated. In a series of 3 electrochemical experiments beginning in 1990, Melvin Miles and his colleagues found a nuclear product that matched the heat energy generated in the cell. The work confirmed the nuclear nature of an as-yet unknown atomic mechanism and provided a major clue to the origins of a next-generation nuclear power.
I was always a skeptic. You have to be a skeptic. So I was surprised. I was surprised that we're getting results. We had evidence for the nuclear product that everybody was saying. If there's a fusion reaction, there has to be a nuclear product. In that fall, I had heard that Julian Swinger was proposing, because nobody was finding neutrons or gamma rays, there could be a D plus H reaction, deuterium plus hydrogen, going to helium-3, and that does not give neutrons or gammas. So I thought, well, that might be the nuclear product. Based on what Julian Swinger has said, I decided that would be interesting to try to find helium-3, because there's not very much in the atmosphere, and that would be quite decisive if it were produced in the experiment. The cell itself was a small test tube. It was filled with about 18 milliliters of electrolyte, not a lot. It was rather small. And it was inserted into another glass tube, was bigger, and in between the two we filled it with water. So, and we measured the temperature in the second liquid. So the cell acted just as a heater. Surrounding that was insulation in a plastic container, and that was our calorimeter put in a constant water bath. The palladium was at the center of that test tube, and the counter electrode was the platinum wire, actually platinum and rhodium counter electrode. I used the same electrodes 3 or 4 different times, and each time they give excess heat. So I knew that we could probably get excess heat, and we just needed to collect the gas samples coming off for helium-4 analysis and helium-3. The gases coming off did not go into the atmosphere. They went through a flask where we collected the gas. It went in and then it came out. The exit was through an oil bubbler, so it comes out as a bubble in oil and then bubbles through the atmosphere. So the atmosphere cannot flow back through the oil. So there's no way that air could flow in. It's closed in the sense it's bubbled through oil. And also it's under positive pressure because the oil bubbler, we had a little higher pressure inside than it was outside. So the tendency would be for something to flow out, not flow in, if it found a place where it could do that. And when we first put the flask in position to start with, then we would pass this boil off nitrogen through the whole system for maybe 30 minutes or so. Just flush everything out. Make sure, because when you put a new flask on, it probably has air and a little bit of helium-4 in it. So you would spend 30 minutes flushing before you even worried about doing any measurement. But you leave the flask often in place for a week or more, at least several days before you would disconnect it. And when we had a good excess heat effect and decided to collect the gas, we would just close the inlet valve on the flask and close the outlet valve on the on the gas and trap it inside and remove it from the line. Overnight, it would be shipped to Texas, and the university had a person dedicated to mass spectrometry. So Ben worked with him. Ben had some good ideas about how to pass it over activated charcoal at liquid nitrogen temperature, so the D2 would be slowed down, and the helium-4 or helium-3 or helium-4 would not absorb on the activated charcoal at liquid nitrogen temperature, and it would go on into the mass spec first. And so they don't go in at the same time, and so we didn't have to worry too much about contamination and problems with D2, which also has mass for it, because it would be slowed down and be separated.
A search for helium-3 required extra precaution to prevent contamination of helium from the atmosphere. The entire system was self-flushing and under positive pressure. While Navy labs were generally well equipped, these flasks were then taped and shipped by express mail to postdoc Benjamin Bush at the University of Texas, Austin, where a sensitive mass spectrometer would measure the helium in each flask. To eliminate any bias by Bush, the flasks were coated with the birthdays of Miles's friends and family.
So he never knew which flask had excess heat and which one didn't. And we had sometimes you had large excess heat, sometimes small. And it turned out in analysis, when we had large excess heat, we found more helium. We couldn't put a number on it because we didn't have it quantized. But the ones with more heat gave more helium, and the ones with less heat gave less helium. We found that there's a correlation also. And if there's no heat, so even in this experiment, early on there was no heat, and that sample had no helium. So when there's no heat, there's no helium. When there's large heat, there's large helium. When there's smaller heat, there are smaller amounts of helium. And, though we didn't have the accuracy to put a number on it. We guessed at the accuracy, but we were off by about a factor of 10. We first ran controls in January, ran water, and we did not see excess heat, and those did not produce any helium-4.
Cells that made excess heat all made measurable helium. Without knowing exact numbers, the amount of helium followed the amount of excess heat. Higher excess power generated higher helium. When there was no excess power, there was no helium. But it wasn't helium-3, it was helium-4. Since the atmosphere contains a small portion of helium-4, how could we be sure no helium from the atmosphere contaminated the flasks?
If any air had leaked in, the mass spectrometer would have gone off scale for helium-4, because we're measuring parts per billion, and helium in the air is parts per million. The only way helium could get in, it could diffuse in, but that's very slow. We later found that was not fast enough to affect our results.
Diffusion of helium through the glass flask or rubber tubing was the only way helium from the atmosphere could enter the system. Later experiments would show that this diffusion is too small to affect the results that pointed to a possible reaction pathway.
And you do a calculation, the amount of heat that we were getting, if you're getting 100 milliwatts of excess heat, just by the calculation of the D plus diffusion reaction, you'd expect in that flask, over that time period it takes to fill a flask, you'd expect about 5 parts per billion, and that's about what we're getting. We were getting about the right amount based on the amount of excess heat that was measured. Mm-hmm. You have to have products to prove a reaction, and a nuclear reaction, you have to have some nuclear product, and nobody knew what that was. It was not neutrons, but everybody was looking for neutrons, and it was not helium-3 because we did not find helium-3, so it was helium-4. I mean, this is not the only explanation, but the most likely one, I think, was D plus D fusion going to helium-4 in energy that was captured inside the cell, not a gamma, because if it's a gamma, it's 23.8 MeV gamma, and that would go through the cell, out the cell, through the walls of the building, into the next building. It could go a long ways away before it could be detected. So gamma would take all the energy away, and you would not be necessarily measuring excess heat. But somehow that energy in a cold fusion experiment gets converted to heat in the cell.
There are several fusion reaction pathways that take deuterium to helium, each making a different amount of energy. The number of helium atoms that Miles and Bush were counting, and the excess heat measured, matched closest to the energy corresponding to simple deuterium fusion. But unlike hot fusion, there was no dangerous gamma photon. The cold fusion reaction made heat instead.
So I was hoping Stringer was right. I was hoping it was D plus H going to helium-3 and no neutrons, no gamma rays. That's what I hoped for, but that's not what we found. Well, shortly after that, we started getting visitors that wanted to come check on us. Brian Oliver, he was working down near L.A. for Rockwell International, and he was the foremost expert on helium measurement in the United States. And he came and talked to us, and he saw what we did, and he did not have much criticism, but he wanted to do his own studies. So that was our second series of experiments, was to get samples and send them to him. The trouble is, we had ran the controls in regular water, so they were contaminated by then with regular hydrogen. So we tried new electrodes, and we could not get the excess heat. We went almost the rest of that year, 1991, trying to get a excess heat effect to send to Brian Oliver, but it took us to almost the end of the year before we got an electrode. We got another Johnson Matthey wire. It was 1 millimeter diameter, smaller, and I finally got excess heat with that. Not a large effect, not as large as I wanted, but in one sample we collected at 100 milliwatts. Another sample we collected at 50 milliwatts excess power, and the third sample was 20 milliwatts of excess power, which is kind of borderline, really, based on my calorimetry. What he did, he would measure the helium diffusion into flask each day for over 40 days. He got a straight line, and he extrapolated back to when we disconnected the flask, and that would be the amount that was in there at the time we disconnected the flask. The one with 100 milliwatts gave the highest results. The one with 50 milliwatts gave the middle results. The one with 20 milliwatts gave the low results. We did not tell him which flask was which. We reported to Dr. Legowski at the University of Texas. And Brian Oliver did not tell us what he had measured. This was reported back to Professor Legowski at the University of Texas, so it was double blind. He did not know our results. I didn't know his results. But it came out exactly, fit exactly what we had measured. The more heat, we got more helium. And he was measuring to 0.1 parts per billion, accurately, 0.1 parts per billion. There's a little bit of helium that comes through a thick rubber tubing, so there's a little bit of background. I later found out what that was. So a couple of years later, I subtracted the background, and I got all three came very close to the expected value of 2.6 times 10 to the 11th helium atoms per second per watt. I came very close to what you'd expect with the D plus D reaction.
And quite a number of efforts were made to find helium, and they did in fact find helium. But here's two that made a correlation between the amount of energy and the amount of helium. This is the amount of helium that should be detected, that is the helium to watt second, or the amount of helium to the amount of energy. That should be based upon the mass change in going from 2 deuterons to a helium. And this is the data. These are two different data sets. The open circle points were made first. They have a somewhat larger scatter. That was done with an isoparabolic calorimeter. Later, somewhat better work was done with a Seebeck calorimeter, somewhat less error. But you'll notice that they are in basic agreement. But
that was the most exact measurements that I had ever had done. The top expert in the United States, Brian Oliver, measuring the helium content at the time 0 when it was disconnected, and within 0.1 parts per billion. And there was at least 10 sigma difference between the different experiments. The first set, we had large excess heat effects, some of the largest I'd ever seen. But we had, the helium measurements were not as accurate as the second set. The second set, we had smaller excess heat effects. The second set was much more accurate helium-4 measurements, the most accurate I ever had done.
The tiny amount of excess heat in the second experiment made an extraordinarily small amount of helium. Still, an expert in helium measurement confirmed the earlier results. To within 1/10 of 1 part per billion, the amount of helium followed the amount of excess heat. But critics weren't listening.
Well, because that was always the criticism, is that helium can get in, helium can diffuse through glass. That's their argument. Even though we showed the rate is so slow that it could not have affected any of the results that we had. In fact, Brian Oliver took account of that when he measured the helium increasing with over a 40-day period. He was measuring the diffusion and extrapolating to zero time when no diffusion could have taken place. This was a year or two later, and nobody was paying much attention anymore to cold fusion. That's the problem. You didn't get a lot of attention, but except in the conference publication. To dispel any questions of helium diffusing in, Ben Bush, he was with me working at China Lake. We wanted to do an all-metal system. We designed these flasks. Ben Bush did a lot of work on that. But it had a metal-to-metal seal. Even the seal does not use anything other than metal against metal. There's no way helium can get in because the metal doesn't allow it. Then Ben Bush left before we did the measurements. So the next year, when I was getting excess heat, I was collecting samples in the metal flask and shipping those off to Amarillo, Texas. They could measure accurate enough that even when there was no heat, they could measure a background. The background was maybe 2 or 3 parts per billion. And then when I had excess heat, I'd get up around maybe 9 or 10, 11 parts per billion. And their error was plus or minus 1 part per billion. That was the background I later used to subtract off the second set of experiments. I subtracted the background, and when I did that, I got very close to the 2.6 times 10 to the 11th helium atoms per second per watt, if you want to put it in terms of a rate. And that's what everybody tried to prove, that it is close to that number predicted by theory.
Deuterium fusion to helium-4 is accompanied by 24 million electron volts of energy for each helium produced. There should be 260 billion helium atoms created each second for every watt of power generated. But these 3 experiments showed slightly less than that amount. Why wasn't the amount of helium found exactly matching the excess heat measured?
One reason, the excess heat is not exact. The second reading, measurement of the helium is not exact, so you're going to have experimental error in both of those. And the third reason, it's not exact that all the helium escapes from the palladium. Some can remain trapped in the palladium. So you have all the 3 possibilities. I'm surprised it came as close as it did. But critics claim that because it didn't come closer, it may be not correct.
That they are in basic agreement, but they're all lower than what's expected. They're lower on average by a factor of 2. And that fits with how we understand the process to work. The process takes place on the surface of the cathode. The helium made there has 2 choices. It can diffuse inward and be captured and not detected, or it can diffuse outward towards the surface. It'll go off then as a gas and then be detected by the later analysis. And there's a 50-50 chance of it going in either direction.
I think it came as close as you can expect, based on the experimental error of both excess heat measurement, excess power, and the helium measurements, and the fact that not all of the helium can escape necessarily. So you don't get an exact number. I'm not surprised at that at all. A fourth reason that I left out is that we're assuming everything is due to D plus D fusion. There might be a side reaction forming tritium, for example, and that would change the value, the number you get. So you will not get exact value. You get the exact value. You have 100% of the reaction being D plus D fusion. You have no error in the helium measurement. You have no error in the excess heat measurement, and all the helium gets out. Then you might get an exact number. But if there's some other reaction going on as well, then it'll be different.
While error occurs in all types of experiments, the correlation between excess heat and helium in palladium-deuterium systems has been reproduced many times since.
There were other people that, I think another name is Gozzi in Italy, later reported helium-4. Bacchus reported helium-4 found in the palladium based on Brian Oliver's work. Brian Oliver did the measurement, and then later another person is Arata of Japan. Danino and other people in Italy also found helium-4. They did a very good job. This is quite a few years later. I think the best evidence that I was correct comes from Mike McCubry, experiments he did at SRI. They had a closed calorimetric system where they recombined the D2 and the O2 so that the gases never escape. So they can keep collecting the gas, and the helium can keep increasing and increasing over time. And so he could show how the helium increases over time because it doesn't flow out of the cell. It keeps building up, and it even gets higher than the room concentration of helium-4. It gets above the 5.2 parts per million helium-4 in the room. So how could it diffuse in when you're higher inside the cell than outside? I would say that's the most substantial proof that what I did was correct. The first set of experiments measured by the University of Texas. The second set of experiments measured by Brian Oliver at Rockwell International, top expert in the country for measuring helium-4. And the third set ran in metal flasks where helium could not have diffused in because it was all metal system, and that was measured by the Department of Interior Laboratory in Amarillo, Texas. And all those experiments agree. I mean, there's helium-4 measured there's when you have excess heat. And with no excess heat, you don't see helium. An exact calculation can be done mathematically. It's complicated, but it comes out that to get the right results 30 out of 33 times, the chance of that happening just by random is 1 in 750,000. And a simple way to think of that statistics is if you were flipping a coin and you want to predict heads or tails and get it correctly, if you could do that correctly 30 out of 33 times, that would be similar to that results that I had. And that would be rare that you'd ever get that, right, by chance, right.
Experimental evidence shows excess heat is commensurate with the amount of helium produced in palladium-deuterium systems. While there is yet no definitive theory that describes the reaction, most of today's leading theoretical models predict helium, though sometimes corresponding to different pathways.
Preparata, ahead of my experiments, predicted helium-4 would be the major product. Scott Chubb and Talbot Chubb came out with a prediction of helium-4 prior to my experiments. Again, I didn't know about it until later. There's Takahashi's process with 4 deuterons coming together. Kim at Purdue, his theory predicts helium-4. Peter Hagestein explains production of helium-4. You could add Ed Storms. He predicts helium-4 as well. I think the only product that it could have been, in retrospect, because it was so hard to find, would be helium-4. But no other product could escape detection for so long as did either helium-3 or helium-4, because those are very difficult to detect. The amount is very small. You have to have very accurate mass spectrometry done. You have to be able to measure down to parts per billion or 0.1 parts per billion, and unless somebody has real expertise to do that, and you had to go somewhere. I had to go somewhere where that expertise existed. They couldn't do the experiments in their own lab.
The China Lake Research Program closed in 1995 after losing funding. Once recognized for his outstanding work, Dr. Miles was told to report each morning to the stockroom clerk for inventory. He chose instead to go to a new lab in Japan, where he again reproduced the excess heat effect using the co-deposition method. Today, further reproduction of these experiments hopes to convince the broad mainstream of science to once again look at this work and help to uncover a new phenomenon of nature and a green solution to our global energy needs.
Yeah, if you work in this field and you see the effects, and you know it's real, you know it's very important, and anything else is much less important in your mind, and in truth really, in reality, is much less important, much more important than battery research. And so that's what you want to do. You want to do something that's as important as possible, and that was cold fusion. And that's why I wanted to do this.